if you didn't misclick on this video, then you'll notice that this is going to be about cross products. They're kind of weird. The rundown is essentially that they are orthogonal to two vectors, always orthogonal. It requires 3 dimensions. So if we have two like this, like that, it's going to come out like this or like that. You can know it based on the right-hand rule. Let's talk about how you can get the magnitude, because actually getting the cross products is going to require for us to take the determinant of the unit matrix. So for two vectors A cross B, if you want to find their cross product's magnitude, so if you want to find that, what you can do is multiply magnitude of A times magnitude of B, and then sine of theta between them. So it values orthogonality because remember, sine maxes out at a pi over 2 and negative pi over 2. Yeah. And so that means if the vectors are the same, your cross product's going to have a magnitude of 0. And if they're orthogonal, it's going to have a magnitude that is just their product. Now when it comes to actually getting them, I could do it symbolically, but I'm going to do it numerically because I know that satisfies a lot of people, getting a number answer and not a mess of an answer. So let's just do 1, 2, 3, 4, 5, 6 because it's easy. So 1, 2, 3, cross 4, 5, 6. So we know it's the determinant of this matrix. So I, J, K, 1, 2, 3, 4, 5, 6. And it must have the first vector on the second row, the second vector on the third row. And, well, I believe I've heard that you can have that two swapped, I think. And so then, to take this determinant, what you want to do usually is have I and J repeated, and then you have 1, 2, 4, 5, and then that lets you take your rows. So, how do you take a determinant? And you subtract these from that original one. So it's 12i. I'm going to denote hat. I should have put a hat on all of these. That's how I denote that they're a unit vector. However, it's okay. And then we have plus 12 j hat plus 5k hat. And then it'll be minus 6 j hat plus 15 I hat. 15 I hat plus k 8 hat. 8k hat. So that gives us that. You can rearrange that so it's ijk. So that's a really poor 16. There. And so do your subtraction, that gives you negative 3 I hat, negative 4 j hat, and negative 30 k hat. And so that is the cross product. If you were to plot them out, you'll notice that it is orthogonal. Cross products matter because they can give you your angular momentum vector. That is your radius times your momentum. That is the cross of your momentum vector and your radius vector. So this is where we get into applications. Application. So we know that I'm not going to remember the right letter, so just know that this is just to note it like a mathematician. Theta momentum equals our normal momentum. No, that's wrong. It's the radius crossed with it. Radius crossed our normal momentum vector. And we should denote they're all vectors. Same with torque. Torque vector is equal to your radius vector crossed with your force vector. Let me see if I can think of any other things. Yeah, I mean, I guess I don't want to give this example because it is a special example, but with Faraday's law, for inductance, you have the divergence of the electric field equals 0. That is, I guess, a very special denotation. And so this is called curl right here. It's something that will be mentioned later. However, that is not what these mean. It's what this notation means with the Laplacian and the cross product. So, I can't think of any problems on my head, but we could plot some. So we have our radius vector, so that's our vector. Then we can have a point mass with some angular momentum. With some momentum. And then we could get our angular momentum, which is then going to be what happens if we have that. We have this point right here in space. We have that radius. We have some kind of angular momentum and some kind of normal momentum. And our angular momentum is going to be a right-hand rule. So with R and P, it's going to be that way. That way, I think. The half's going off in this direction, not right. It's going in this direction, not in that direction. So it is kind of like that is how it looks, kind of going through the plane. It's not parallel. No, it is parallel with Z because these aren't in Z. So yeah, it's going to be orthogonal to both of them, and it's going into Z if that's Z. Same thing goes with our torque. If we have some particle, we have a force on it, just say it's perfectly like that. We then go into multiple dimensions. It's not going to be great for demonstration purposes, I'm sorry. Actually, I'm just going to fix it. There we go. So we have this, then go up some distance, and then probably be like that-ish. That's our force. And we have a radius vector. We have a radius vector. And then from there, well, we have something that is going to be orthogonal to both of them. So these aren't inherently orthogonal, but this will be. So if you take both of them, there will be a 90-degree angle between them both and that vector. And so then with curl, this is a special case. I'm not going to say any more than it is good for describing how much a vector field goes around a point. And so in this case, it's saying that a lone charge, like this right here, is not going to have none of that. Which would then let you kind of inductively say, okay, well, magnetic fields have to have some curl, which they do. So there.